Okay, similar to a previous problem, let's say we have a particle of charge Q star, and it experiences an electric potential difference of magnitude phi star, and it travels a length, let's say L, and it has a mass m naught, and we want to know, let's say that the electric field, right, the E field, doesn't change with distance, so it's always some constant value, and the question is, what is the magnitude of that electric field through which the particle passed if it starts at rest and speeds up to some value, let's call it Vf for V final. Okay? So under these circumstances, our work-kinetic energy theorem looks as follows. So the right-hand side is the same as in the previous case, right? We have the final kinetic energy, which is 1/2 m naught V final squared in this case, and everything is known, right? Minus the initial, but the initial is 0 because the particle starts at rest, and the work done on the particle is because the electric field is a constant, right? So the work is just the integral of the electric force over the distance that the particle travels, which is in this case the value of the charge Q star. Right, it's Q star times the constant electric field that we don't have. So it's Q star times the magnitude of the electric field times the distance traveled, which is L. And so that's the work in this case. It becomes force, right, times the distance, force times L. And the force is unknown because we don't have the electric field. But we can write it here as Q star EL. And we see that the only unknown is the magnitude of the electric field, which then becomes m naught V final squared over 2 Q star L. And that's the magnitude of the electric field. Let's say that we have a particle of charge Q star that is already moving with a speed let's say V naught, starts with the speed V naught, but this time the electric field is opposite. So there's an electric field that is opposite to that direction, so it's that way, but we know that it travels a certain, it goes through a potential difference of magnitude psi star, and it's the same particle, so it has charge Q star, and its mass is the same, so it's m naught. And we want to find, let's say we don't know what the initial speed is. Let's just make it v. And the question is, what is v? What is the initial speed that the object has if it manages to travel through a electric potential of magnitude psi star before it comes to a stop? So again, it's the work-kinetic energy theorem, which looks like what? So in this case, delta K is final kinetic minus initial. The final kinetic is 0 because at the moment it comes to a stop, it has 0 speed. Minus the initial, we have the 1/2 m naught times the unknown speed squared, and that has to be equal to the work. But the work, notice, has to be negative because the kinetic energy difference is negative. And so in fact, negative work slows the particle down, and we can see why this kind of a thing here is negative, because the electric force is in that direction, whereas dr, right, so the velocity is this way, and the object travels in the direction dr, which is 180 degrees, and so we have a negative sign emerge from the dot product. So here we get, in terms of the known charge, we have Q star times the electric potential difference through which it traveled, but this has to be negative because the work is negative. And so we can solve for the initial speed of the particle as 2q star psi star over m naught square root. Right, that's the initial speed.